The purpose of a coordinate system is to coordinate motion between multiple different motors, all in a single controlled fashion. So in a coordinate system, you'll typically have multiple different motors, each assigned to axes, and you'll issue commands to those axes. They can be grouped together, they can be started and stopped at the same time. You can set them so that they all have a given feed rate. You can set it so a tooltip has a given feed rate, and that tooltip is made up of axes. It's basically just the easiest way to coordinate motion between multiple different motors is to define some relationships between them in a given coordinate system. There are two different ways of defining the motion in a coordinate system. They are mutually exclusive. If you choose one, you can't use the other. For some axes, you have to use all for one or all of the other. And they are using axis definition statements, which is the first one we'll go into. It's fairly simple. You just assign a direct linear relationship between some number of motors and some number of axes. And then the other one is a kinematic subroutine, which is the more powerful way of doing it. It gives you a lot more control, but you need to define both the forward and inverse kinematic relationships between your motors and your axes. For a simple linear relationship, as we'll see in a minute or two, that is no work really. It's very easy to invert the equations. But if you have a more complex system, multi-axis system, where you have motors mounted to other motors effectively, it can get to be a more complex system, and as such it may be more work to generate those equations. So generally speaking, we recommend that you put all of your coordinate system definitions, all of your axis definitions, all of that sort of thing into coordinatesystems.pmh, which is in PMAC general script language, global includes, and then make this file in the global includes folder of your PMAC. This parameter, since I just explained some of this stuff, motor, sys, etc., introduces a new prefix, which is coord_x. You can have multiple different coordinate systems, so this is how you address each one of them individually. The general concept for a coordinate system. You will come up with some relationship between your motors and your physical system. If it's a linear motor you have, it could be easy enough as 5,000 counts of this encoder is equal to 1 inch of travel. It could be much more complex than that, but the general purpose of setting all this stuff up and all the kinematics and all of the axis definitions is so that the operator of this machine can come in and say, I want the x-axis to move 3 inches, and the PMAC will take that command, your axis command here, feed it through either your axis definition statements or your inverse kinematic subroutine, and it will end up with some motor commands. It may be just one motor that's being commanded. It may be a virtual motor, which is a motor that doesn't actually exist, but it's used for calculation purposes. Or it may be a series of multiple different motors. But the key is the user only has to command the axis. The PMAC then takes that command and figures out what all of the motors need to do to respond to that appropriately. It will then use those motor positions, feed it through either the automatically inverted axis definitions, if you chose to use axis definitions, or the forward kinematic subroutine, if you chose to use an inverse kinematic subroutine. Do the calculations, and from the motor positions, it will figure out where all of your axes are to start with. Now, the CPU itself, the PowerPMAC CPU, can control up to 256 motors at a given time. Those are going to be split up, however. It can control, I believe, 128 coordinate systems, each one with 32 axes in it. Now, motion attributes are specified in terms of raw counts and milliseconds in general, which is to say, normally when you're issuing a motor command, it's in motor units, and if you're issuing a motor command that's time dependent, such as a velocity, it'll be in motor units per millisecond. Axes, on the other hand, are generally commanded in the units of whatever you want them to be. It'll typically be whatever units you usually work. If that's inches and feet, it could be that. If it's millimeters, meters, centimeters, kilometers, whatever you want to use there, it'll be in that. Additionally, the time parameter, same thing. You can continue to use milliseconds if that's convenient to you. However, you can also scale that up to seconds, minutes, hours, or even down to microseconds, nanoseconds, what have you. So axes are really meant to be the user-accessible way to command motion. The axes are going to be specified by letters. The first 9 are ABC, UVW, and XYZ. However, there are additional axes, up to 32 total, if you double up on letters. So in addition to these 9, there's AA, BB, CC, DD, all the way through to ZZ, with the exception of II, JJ, and KK. Those are reserved as they are vectors in 3D space, if you're doing some stuff in 3D space, which I believe we'll cover later this week. If not, it's not frequently used, frankly. So A, B, and C, and AA, BB, and CC are predetermined as being rotary axes. If you have a spindle or something like that, you'll almost always want to assign it to one of those 6 axes, whereas XYZ, XXYYZZ, UVW, UVVWW are, because those are going to be the standard Cartesian axes, XYZ, and then also UVW for expanded, more Cartesian axes, we allow for real-time 3x3 matrix transformations for rotations or whatever sort of transformations you need to do. If you have a specific question about that, I believe it may be covered later this week. If not, feel free to ask when we get to the matrix transformation section, which we will get to later this week. So, as I mentioned, coordinate systems PMAC can support up to 128 coordinate systems at the same time. You can manually limit the number of coordinate systems it has, which reduces on computation time. If you want to set sys.max chords to a lower value, if you set it to 128, PMAC is going to go through, admittedly nominal, but calculations for all 128 coordinate systems. If you set it down to 2, because that's how many you're using, it speeds up PMAC a little bit. A coordinate system can have up to 32 axes. Again, that's these 9 plus these 26 minus II, JJ, KK. It synchronizes the motion between the axes if you have different axes in a single coordinate system. And coordinate system 0 is the default coordinate system that all unassigned motors are in. So if you ever issue just a motion of a motor, that motor by default is being assigned in coordinate system 0. As a couple of students found out with the percent command, which affects the time base is coordinate system specific. So if you are just issuing a time-based command in the terminal window and you haven't done anything, that time-based command is being issued in coordinate system 0. So as I mentioned, this says 3, I'd argue there's 2, but there's different types of axes. There's the standard Cartesian axes, XYZ, UVW, and they permit circular interpolation amongst any of the standard 3D planes, XYZ, and at different angles. Different angles are being accomplished by the real-time 3x3 matrix transformations. On the other hand, in addition to Cartesian, we have rotary axes, which are ABC, AA, BB, CC. Those ones are special in that because it knows those are rotary, you can have them roll over. You can say that I want my A axis to just roll over when it gets to 360 degrees and go back to 0. So if you set chord.pause rollover, that sets the position at which that one will roll over and it'll restart to 0. Additionally, you can use chord.alt feed rate. A little bit later, we'll learn about the frax command, the feed rate axis command. It determines how all of the axes move, what speed they all move with. You can use chord.alt feed rate. Basically, if you have a machining application or something with a spindle that you want to keep moving at a very high speed, and then you want a piece, an XY table, to move at a lower speed below, you can use chord.alt feed rate to control the feed rate for the spindle, and you can use the frax command to control the feed rate for the XY table. Again, we'll get into that, and it will make sense a little bit later. Frax, as I said, feed rate axis, by default looks at your X, Y, and Z axes, which means if you issue a frax command and a feed rate, F10 say, that sets a feed rate of 10 units per second, and it will calculate that based off the motions of the X, Y, and Z axes. Again, when we get into motion programs, it'll be explained a little bit more. Now, you can define axes with different combinations. You can define a single motor to a single axis. You can define a single motor to a linear combination of axes. It's equal to X plus Y. You can define multiple motors to one axis if you have a gantry with motors on both sides of it, for instance. Multiple motors to a combination of axes if you have, say, motor 1 and motor 2 are at 45-degree angles offset from your X and Y axes. You'll see in a second, but motor X is a combination of X, or motor 1 is X and Y, motor 2 is also X and Y. You can have a phantom axis, which is an axis that exists for computation purposes, but no motor is actually assigned to it. If you want to output a sine wave, for instance, you can issue a circular command and have one of your axes be a phantom axis, so it doesn't actually command any motion in that, and you end up with just the harmonic motion. And they can be assigned if they're directly linear. If they're nonlinear, you need to provide PMAC with the kinematics. So, what that all means, over here on the far right, or in the far left, we have coordinate system 1, which is made up of motors 1, 2, and 3. Each of the three motors, X1, 2, and 3, are directly assigned 1-to-1 to the axes X, Y, and Z. So in coordinate system 1, we have motor 1, which controls the X-axis, 2 controls the Y-axis, and 3 controls the Z-axis. And over there, we're running motion program 1 is running that coordinate system, and it's controlling those motors. That's fine. Next, we have coordinate system 2. Similarly, coordinate system 2 uses the X, Y, and Z axes, but now it's using 4 motors. It has 2 gantries, I'm going to say. We have one gantry in the X-axis, which is controlled by motors 4 and 5. In this case, we see, because they're both tied into X, whenever I issue X10, that means motors 4 and 5 are both going to move. Then we have our Y-axis, which has absolutely nothing assigned to it. We can use it for calculation purposes. We can use it for circular moves, for spline moves. We can use it for feed rate purposes, but we have no motors actually assigned to it. So if we issue a move in the Y direction, no actual motion would happen. And then we have our Z-axis, which I'm going to say is another gantry in the opposite direction from the X-axis that again has 2 motors assigned to it. Those 3 axes, X, Y, and Z in this case, make up coordinate system 2. In coordinate system 2, we're running motion program 2. Now we also have on the far left a third coordinate system 3, again, X, Y, and Z axes. The Z axis is controlled by motor 10, straightforward 1-to-1 with some scale factor theoretically, or an offset, or a couple different things, but it's a linear relationship. Now, motors 8 and 9 are combined together to control axes X and Y, which means if you move just X or just Y, you have to be prepared for both motors 8 and 9 theoretically to move. If you move axes X and Y in a specific way, theoretically one of the motors or both the motors may not move at all, but if you move either axes, you have to expect that both motors may possibly move. Now, in coordinate system 3, we are also running motion program 2. Motion programs are not coordinate system specific. You cannot run multiple motion programs at the same time in one coordinate system, but you can run the same motion program at the same time in multiple coordinate systems. Each coordinate system is its own separate thing with its own separate motors and its own separate motion, so you can't run 2 different motion programs at the same time, because then you may be commanding the X-axis to move forward and backwards at the same time. But motion programs, when written properly, are generalized enough that you theoretically could write a motion program that works in this coordinate system or in that coordinate system there. Depending on your axis definitions, it may do something completely different, but because the motion program only cares about axes, you should be able to run it in any coordinate system that has the same axes defined. So, for a coordinate system, if you want to come to a blank coordinate system, know that you're coming in with no axes definitions, you might want to begin by issuing undefined, then undefine all. Undefined clears the axis definitions of the currently addressed coordinate system. Undefine all clears the axis definitions of all coordinate systems. So just a blanket undefined on every single one of the coordinate systems. If you have a motor that you want to remove from a coordinate system, you can say £n assigned to 0. Doing that means it is assigned to no axis at all in the coordinate system and therefore is removed from the coordinate system. So an example could be this here. We begin with issuing an undefined all to make sure that we're not modifying anything. We're starting from scratch. Then we have and1, coordinate system 1 is the coordinate system we want to address. Then £1 assigned to x-axis. So if we move the x-axis, that's going to move motor 1 and nothing else. Now that we've done that, we want to go to coordinate system 2, so we issue ampersand 2. Then we say pound 2 assigned to x, pound 3 assigned to y, and pound 4 assigned to 0. If in coordinate system 2 we now move that x-axis, rather than moving motor 1 like it would have in coordinate system 1, it now moves motor 2. The y-axis now moves motor 3, and motor 4 is not in the coordinate system at all. So it's in no coordinate system, but it is specifically undefined from coordinate system 2 if it had a definition previously. Now, an axis definition statement, it could be as simple as pound 1 points to x, or it could be a little bit more complex. In this case here, we have motor 1 is being assigned to 10,000x plus 500. What that means is if I issue x1, motor 1 is going to take that and see this is a value of 1 right here. So motor 1 is going to go to 10,000 times 1 plus 5,000, or motor 1 goes to a value of 15,000. If you want, you can have a scale factor. You don't have to. If you want, you can have the offset. You don't have to. Many times you'll have a scale factor, but you won't necessarily have an offset. However, there are times when you want the offset there too. Now, you can also do a linear combination, which is something like this. Motor 1 points to 1000x plus 5000y. So now, if I move my x-axis to 1 count, motor 1 is going to go out to 1000. If I then on the next line issue x0, y2, motor 1 may dip inward a little bit, but it will end up at the exact same spot of 1000 counts, because with x value of 0, we have 1000 times 0. With the y value of 2, though, it's plus 500 times 2, 1000. So if you have just a simple scale factor, the axis definition is basically just a unit conversion, converting between the encoder counts of the motor to whatever units you want to use for your axis. Now, on the left here, we have some legal statements, and on the right here, we have some statements that PMAC won't necessarily tell you are wrong, but will not behave like you want them to. So on the left, we have pound 1 points to x in coordinate system 1, and pound 2 points to x in coordinate system 2. Perfectly fine. If I issue an x command in coordinate system 1, motor 1 will move. If I issue an x command in coordinate system 2, motor 2 will move. It doesn't matter if I issue them at the same time or separately. Nothing will go wrong. The motors will do their things. On the right, however, we have in coordinate system 1, motor 1 assigned to both x and y separately. That's a problem if it's on two separate lines like that, because now I may move x to 10 and y to negative 10. Motor 1 now needs to be in both simultaneously 10 counts and negative 10 counts, plus possibly a scale factor and offset stuff. But assuming that we don't have the scale factor or the offset like this, then we have motor 1 needs to be in two different spots simultaneously. What will happen with a case like this is PMAC will issue the three commands, &1, pound 1 points to x, pound 1 points to y. It'll issue those sequentially. So it'll enter coordinate system 1, it'll define motor 1 as your x-axis, and then it will redefine motor 1 as your y-axis. You'll end up with your x-axis not defined at all, not pointed to anything, and motor 1 controlling your y-axis. Now on the bottom here, a different alternative. We can say in coordinate system 1, I want motor 1 pointed to x and motor 2 pointed to x. That's perfectly fine. If you issue an x5 command, motor 1 will go to 5, motor 2 will also go to 5. No interference, nothing physically impossible, nothing has to be in two spots at once. It's just that command of the x-axis will move multiple motors. On the other hand, if we have two different coordinate systems, coordinate system 1 and 2, and both of them have the same motor in them, motor 1 pointing to the x-axis in both of them in this case, that is not allowed, because if you try and do that, you may have coordinate system 1 trying to move the x-axis over here, and coordinate system 2 trying to move the x-axis over here. And again, physically impossible to be in two spots at the same time. If you try and do that, when you try and put motor 1 into its second coordinate system, PMAC will just ignore that. It won't let you do it. It will say motor 1 is already defined in coordinate system 1. It can't be defined in any other coordinate system, so it will not accept that command. Now, if you wanted to switch it, so motor 1 was in coordinate system 2, you could do that by in coordinate system 1, say motor 1 points to 0, undefining it from that coordinate system, and then motor 1 points to X in coordinate system 2, and that's perfectly fine because there's no time at which motor 1 is in both coordinate systems. So, say you have a system, and in this case, we have motor 1 as a linear axis that's going along this line here, and motor 2 is also a linear axis that's going along this vertical line here. They intersect at this point O prime, or that's where your tooltip is located if both motors are at 0. But let's say that those are in encoder counts, not in inches, and those aren't at the 0 of the machine. So, in this case, you may want to have a scale factor to get them from encoder counts into inches, and you'll probably have an offset to get the 0 of the machine at the 0 of the axes. For a case like that, you may want to have some script like here on the left side of the screen, where you have pound 1 goes to 10,000x plus 4,000, 10,000 because we're assuming 10,000 counts per inch, and 4,000 to account for this 4-inch offset, 40,000, sorry. And then motor 2 goes to 10,000y plus 20,000, same 10,000 scale factor to convert between motor units and inch, and 2-inch offset between the 0 value for motor 2 and the 0 value for the y-axis that it's representing. That would be an example of translation and scaling. Now, if you have rotation, say your x-axis is 45 degrees offset from the actual motor that motor 1 is, and in that case also 45 degrees offset from motor 2. And your y-axis is similarly 9 degrees offset from your x, so it's 45 off both those again. You may want to do something like this. Again, let's assume 10,000 counts per inch, but now it's at a 45 degree angle, so we're going to use a scale factor of 7071.07. That's equal to 10,000 times sine of 45 degrees. Now, if I move motor 1, we see my x-axis is increasing and my y-axis is decreasing. That's because if I have motor 1 right here, that's equal to the sum of an x-axis position of here with a y-axis position of here somewhere. So, motor 1 is being defined to 7071.07 x minus 7071.07 y. Now, motor 2, on the other hand, is different because it's going vertically up and both the x and the y-axis vertical component is in the positive direction with respect to that motor. It's equal to the sum of the two. Position of motor 2, value of right here, corresponds to this position on the y-axis and this position here on the x-axis. We see it's positive on both of them. So, motor 2 is defined by 7071.07x plus 7071.07y. I explained that motor-centric. In reality, I should have been explaining axis-centric. An x value of a positive x value of this corresponds to a positive 1 plus a positive 2, whereas a positive y value here corresponds to a negative 1 and a negative 2. But in the end, it's just two ways of looking at the same coordinate system, the same puzzle. So you can do rotation by just making a motor defined to a linear combination of multiple different axes, and you can do translation by just adding an offset onto it. Now, there are also some special definitions, special cases that PMAC has allowed for. If you address a coordinate system and assign a motor number to 0, that is the null definition is what we call it. As I mentioned, that removes the motor from the coordinate system. It removes the motor's association with axes in the coordinate system. It still is defined in the coordinate system, just defined as 0, and it will still use the feed rate for that coordinate system. If you change the time base, it'll still use the time base for that coordinate system, but it can't be commanded by an axis command as it's not associated with any particular axis. Now, if you have a purely rotary axis, a spindle, most often if you're doing some sort of machining on a mill or a lathe, and you have your spindle that you want to spin at some high speed, say you have a vertical mill and you have a moving platform and you have a rotating tool, a spindle. You may want to make sure your spindle is always spinning at a certain RPM while your platform moves around however it's moving. So for a case like that, you would want to often assign whatever axis controls the spindle to S, spindle. You do not use any axis commanded trajectory. It knows it's a spindle. It will still be killed on a fault if you encounter a fault on the coordinate system, and you can jog the motor, or you can use an open loop command with out or C out. But the purpose of it is for you to have the motor in the coordinate system, so you can sometimes use it if you want to move to a specific spot, but generally speaking, it's doing its own thing, so to speak. You don't need to redefine a look-ahead buffer when changing between spindle units versus axis units. PMAC is equipped to handle that. And you can define it in 3 different forms. You can either point it to S, in which case you use the time base of the coordinate system that you're issuing the command. You can define it to S0, which uses the time base of coordinate system 0 always. So you can adjust the time base of coordinate system 0 without adjusting the time base of the entire coordinate system you're working in, and doing so, you'll change your spindle speed. Or you can assign it to S1, which will always have the spindle running at 100% time base. You can alter the time base of the coordinate system, change the time base of the other motors in the coordinate system, but that will always be at full speed. Time base, just a very, very, very quick summary. It basically affects how PMAC sees time itself. A time base of 50, so %50, what that does is it says to PMAC, 1 millisecond to PMAC is equal to 2 milliseconds to us. It's going at half the speed of normal time. So if you have it jogging at 32 counts per millisecond, it will still think it's going at 32 counts per millisecond. It's just that it actually is going at 32 counts per 2 milliseconds, or 16 counts per millisecond. So you can use time base to slow down an entire coordinate system. Very useful for debugging. If you're setting up a system for the first time and you're afraid of collisions, you might run it at 10% time base or something like that, just so everything is moving a lot slower. And if you have a collision, or if you see an impending collision, you have more time to stop it. Very useful for debugging or original system setup if you have a large machine. Now, we've talked about the direct linear axis definitions. The other option is you can point a motor to I, just capital I. What that tells PMAC is it says, for motor 1, rather than using this linear equation I'm going to give you, use an inverse kinematic buffer that I'm going to define somewhere else. When you do that, you will have somewhere else inverse and forward kinematic buffers. You need to have both of them. And they will have the equations that directly relate the motor and the axis. So if you plug in values of the motor, you can get the axis, and when you plug in values of the axis, you can get the motor position. We'll get to that a bit later, probably on Thursday, when we actually go into the kinematics, and we'll go through some of the possible equations and go through a couple examples of that. But we do want to mention right now that it is the other way of assigning axes.